Good. Alright, so first, an announcement like I just said. Announcement. Assignment 3 is due Monday, the 17th, instead of Friday. Okay, so let's start with a summary. We've introduced the Hamiltonian, H, which is a function of the generalized coordinates, the generalized momenta, and time. And it's obtained by taking the sum from I equals 1 to little n over the degrees of freedom of pi qi dot minus the Lagrangian. Okay, where the pi, generalized momenta, are given by di L by di qi dot. We saw that this was a Legendre transform, and so the Hamiltonian H truly only depends on Q and P. It doesn't depend on the Q dots. So we have two ways of doing things. One is with the Hamiltonian using Qi and Pi, and one is using the Lagrangian, which uses Qi and Qi dot. In the Lagrangian formalism, you end up with n second-order differential equations for the equations of motion, whereas in the Hamiltonian formalism, you end up with 2n, but first-order differential equations for the equations of motion. In the Hamiltonian formalism, we treat the Q's and P's on the same footing. So both Q and P's can be thought of as coordinates to describe the system. Whereas in the Lagrangian formalism, the Qi are the coordinates and the Qi dots are just the time derivatives of those coordinates. So the equations of motion were given by Hamilton's canonical equations in the Hamiltonian formalism. And the canonical equations are that the Qi dots are equal to di H by di Pi, and the Pi dots are given by minus di H by di Qi. And so if you solve these, you can get Qi of t and Pi of t, which of course describes the system. And then last time, we looked into a little bit more about this phase space, as opposed to configuration space. And so in Hamiltonian mechanics, the time evolution of a system is given by a path in what we call phase space. And each path in phase space is unique for a particular system with a particular Hamiltonian. So there are no paths in phase space that intersect, because that would mean that a certain physics, so a certain Hamiltonian with given initial conditions, could end up to two different possible final states. And so that would mean that classical mechanics is not deterministic. And of course it is. And so we did one example, for example, of the simple harmonic oscillator in phase space, so a one-dimensional problem. So in phase space, you have to describe the system by specifying both its position and momentum. And we saw that for a simple harmonic oscillator, the path is closed and it's an ellipse. And we saw that different energies lead to different paths in phase space. And so of course you can picture the simple harmonic oscillator oscillates between two extreme values in x, and its momentum is highest when it's in the middle between those two extreme values. So intuitively the diagram makes sense as well. And if we think of this phase space as a fluid, so you can think of a bunch of different systems. So you're given a Hamiltonian that gives you the shape of the flow, and then different initial conditions will put you in different spots on this diagram. And if you look at all those systems, as they evolve in time, they look very much like a fluid. And so the path of these systems in phase space looks a lot like the path of an incompressible fluid. So much so that you can actually apply the equations of fluid dynamics to describe this phase space fluid. And that's what Liouville's theorem was that we saw last time at the end of the lecture. And Liouville's theorem basically says that the system behaves like a fluid. And so in particular, that meant that the divergence of the velocity field was equal to 0. So we could draw the velocity on this diagram. So the velocity is tangent to these paths. Okay, any questions about that?
How did he determine that it was fluid?
So that's the essence of Hamiltonian mechanics. And
ask, how did he determine that it was fluid?
First part?
Fluid in nature. That's weird.
Well, it's sort of the same argument that we just made, right? You can draw the path of a system in configuration space, right? The same system with different initial conditions will have different paths, and those paths will intersect. So you can't really come up with anything intelligent to say about that. However, when you do this in phase space, it's not so difficult to notice that the path of a system in phase space are a bunch of lines that never intersect for different initial conditions. So it looks like a fluid. And so then you can just ask yourself, well, can you apply the equations of fluid dynamics to the system? And it turns out it's the same math. So it's not like literally a fluid, but it's the same math that describes a fluid. Does that answer your question? Or, I mean, it's certainly like a beautiful insight that, sounds obvious after you explain it, but, it took a lot of insight to recognize. So in general, then, if you're solving just a mechanics problem, at this point now you have several tools. You obviously have Newton's second law, you have the Lagrangian and the Euler-Lagrange equation to get the equations of motion, or you have the Hamiltonian description, which we just described, and that's done by first calculating the Hamiltonian from the Lagrangian, and then using the canonical equations. What I forgot to mention, I'm going to run out of room. Where should I put it? Let's put it here. We saw that often, so when the Lagrangian doesn't depend explicitly on the velocities, and when I think that's the main requirement. So let me box it here. We saw that often the Hamiltonian is equal to T plus V, which is the total energy. Okay. That's not the definition of Hamiltonian. The definition of Hamiltonian is this thing above there with the Legendre transform. However, in most cases, when the potential doesn't depend on the velocities explicitly, the Hamiltonian is equal to T plus V. And when the Hamiltonian, we also saw, it doesn't depend explicitly on time, so dH by dt equals 0, then the Hamiltonian is a constant. So the total time derivative of the Hamiltonian is equal to the partial time derivative of the Hamiltonian. That's not true for the Lagrangian, but we showed that it was true for the Lagrangian. Maybe let's add that equation here. We showed that dH by dt is equal to dH by dt. So that's key, right? That means if the Hamiltonian doesn't depend explicitly on time, although it clearly depends implicitly on time, if it doesn't depend explicitly on time, it's actually conserved. Of course, that's the whole reason for doing this Hamiltonian mechanics. Okay, any more questions about that? So now we're going to look at a thing called Poisson brackets, and it's sort of a mathematical artifact that's really neat and ends up being deeply related to quantum mechanics. So it's quite analytical, but then we'll see that it's quite beautiful, and it makes, again, this connection between these symmetries and conserved quantities. So Poisson brackets. So given two functions of the canonical variables, So canonical variables, I mean qi, pi. And those two functions I'm going to call u of qi, pi, and t, and v of qi, pi, and t. The Poisson bracket, I'm going to abbreviate PB, is defined as so we use this curly bracket notation. So curly bracket, oh, that's a terrible curly bracket. Curly bracket u with v is defined to be the sum from I equals 1 to n of di u by di qi times di v by di pi minus di u by di pi times di v by di qi. Okay. So the q's and p's could be x's and px's, for example. And the u's and v's could be h's or l's or v's or any other function. Okay. So this is actually quite an annoying equation if you were to write it out over the sum, right? There are n of these terms. So these Poisson brackets are interesting because they're actually related to the commutators that you have in quantum mechanics. All right, and that's a connection that we'll make sort of at the end of the course. But that at least should inspire you to want to know more about these Poisson brackets. So there are a lot of properties of these Poisson brackets. And I'm just going to write them all out, and then we'll prove a couple of them, and you'll prove the rest in the assignment. They're easy to prove. They're just a matter of applying the definition. And some of them are trivial. So properties of Poisson brackets. First of all, the Poisson bracket of u and v is equal to minus the Poisson bracket of v and u. If you look at the definition, that's obvious. All right, if you switch u and v on the left-hand side, then you get minus what you had on the right-hand side. Okay? Now, the Poisson bracket of a function with itself is equal to 0. And that makes sense, of course, because if you look at the definition and you put u's everywhere, since the partial derivatives commute, then you get 0 identically. If you have the Poisson bracket of k times u, where k is a number, and v, that's equal to k times the Poisson bracket of u and v. K is just the number, or constant. All right, so that's also pretty trivial. If you have two functions, or three, I guess, a plus b and v, so the Poisson bracket of the sum of the functions a plus b and v, that ends up being the sum of the Poisson brackets. A with v plus b with v. By the end of this, we'll be very good at drawing curly brackets. Okay. Now, same thing with the product.
Yeah. If we switched B for A in that last statement, would that still be correct? So A plus B, comma B equals brackets B, comma A plus B, comma B.
V, comma A.
I just flipped them.
Yeah, you should be able to demonstrate that. I think that's true. Yeah, I think you can switch them out. They're easy to prove. In fact, we'll prove that one. And so that's what I was chosen to prove. And then you can see that if you switch it, you'll get the same answer. So with the product, it's a bit different. So AB with V is A times B with V plus B times A with V. If you take the Poisson bracket of one of the coordinates with another coordinate, that's the same as doing it with one of the momenta, and that's equal to 0. However, if you take Qi with Pj, that's equal to delta Ij. Delta Ij, remember, is the Kronecker delta. That's equal to 1 if I equals j, and 0 if I is not equal to j. Slightly more annoying to prove in the assignment will be that Qi to the power of n with Pj is equal to n times Qi to the power n minus 1. I have to double check that one because I feel like there needs to be a delta Ij in there, which is not in the notes. And then we have a function, u, with pi. That ends up being equal to di-u by di-qi. And similarly, if we do a function u with qi, we end up with minus di-u by di-pi. And these are all relatively easy to demonstrate simply by using the definition. All right. And then the last one is called Jacobi's identity. We're not going to use it. So that's a double one. So it's the Poisson bracket of U with the Poisson bracket of V and W plus the Poisson bracket of V with the Poisson bracket of W and U, plus the Poisson bracket of, I'm going to guess, W with U and V is equal to 0. So these are all, they're called cyclic permutations. So it goes U, V, W, and then the second term, you shift everything to the left, and the one that was the leftmost comes to the right, and you continue. Okay. This last one's called Jacobi's identity. I'll make you prove them all explicitly in the assignments. But just to convince you that it's not very difficult to prove it, let's prove this one here. So A plus B with V is equal to A with V plus B with V. Okay? So, if we take the Poisson bracket of A plus B with V, that's defined to be the sum, of di A plus B, the first function, by di Qi, di V by di Pi, and then minus di of A plus B by di Qi times, that should be a Pi, minus di V by di Qi. All right. So that first term, because of the summing properties of the derivative, so that's the same as di A by di Qi times di V by di Pi plus di B by di Qi times di V by di Pi. So the sum from I equals 1 to n. So if I expand out the first term, I have di A by di Qi, di V by di Pi plus di B by di Qi, di V by di Pi. Alright, that's the first term. Second term is minus di A by di Pi, di V by di Qi, minus di B by di Pi, di V by di Qi. Okay, and now you can see that this is going to work. So I'm going to group the A's and the B's together, right? So the sum I equals 1 to n. So first I have di A by di Qi, di V by di Pi, minus di A by di, I'm just rewriting the same terms in a different order. So, di A by di Pi, di V by di Qi. Alright. Plus the same thing for B. I have di B by di Qi, di V by di Pi, minus di B by di Pi, di V by di Qi. And so now I look, I have exactly the definition of the Poisson brackets. And so indeed I have the Poisson brackets of A and V plus the Poisson bracket of B and V. Okay? Any questions? It's tedious, but it's easy. All right. So now that you're experts on Poisson brackets, let's see why we introduced them. As I said, there's a connection with quantum mechanics, and then it turns out they're also related to all this theme of symmetries and conservation laws in classical mechanics. So let's consider, the Poisson bracket of generalized or canonical coordinates and the Hamiltonian. Alright, so that means let's consider the Poisson bracket of Qj with the Hamiltonian. Okay? So I just apply the definition. That's the sum from I equals 1 to n of di Qj, my first function, by di Qi, di H by di Pi, minus di Qj by di Pi, di H by di Qi. Okay? So note a few things. Di Qj by di Qi, that's equal to delta Ij. So in other words, it's equal to 1 if j equals to I, and it's equal to 0 otherwise. So remember, the Qi's and Qj's are like x's and y's, right? So that's like saying that di y by di x is equal to 0. The partial derivative of y with respect to x is 0. And the partial derivative of y with respect to y is 1. Right? So that term is 1 if it's the same coordinate and is 0 otherwise. And for the same reason, the term di Qj by di Pi is also equal to 0. But is equal to 0, period. Because the Qi's and the Pi's should be treated as coordinates of the system, right? So the Px is just another coordinate, so it's like x, y, z, px. So they're all independent of each other. So they all, their partial derivatives between a q and a p is definitely between two different coordinates, and so it's always 0. Okay? And so, given that, then we find that this Poisson bracket is simply equal to di H by di Pj. So the second term in the Poisson bracket is 0. And then this term here is delta Ij. So it's only equal to 1 when j equals to I. So it selects in the sum of terms over I, it selects out the term where I equals j. And so that's why you end up with a j. Any questions about that? So it's similarly trivial to show that the Poisson bracket of Pj with h, if I write out the sum, that's the sum from I equals 1 to n. I have di Pj by di Qi, di h by di Pi, minus di Pj by di Pi, di h by di Qi. So similarly, we have this term here must equal 0, and this term here is equal to delta ij. That's a third relation, which I didn't write up here, but it would be that di Pj by di Pi equals delta ij. And so again here we're left with minus di h by di Qj. Now compare this with the canonical equations. So the canonical equations, remember, are that Qi dot is equal to di h by di Pj, and by Pi. And Pi is equal to minus di h by di Qi. Alright, that's the canonical equations of motion. Let's compare that with what we just found. We found that the Poisson bracket of Qj with h was di h by di Pj, and we found that the Poisson bracket of Pj with h was minus di h by di Qj. So we find an alternative way to write the equations of motion using these Poisson brackets. So an alternative way is to say that the time derivative of Qi is given by the Poisson bracket of Qi with h. And the time derivative of Pi is given by the Poisson bracket of Pi with h. So that's pretty neat, right? The time, at least for the coordinates, it seems like you can find how they evolve with time by simply taking the Poisson bracket of the coordinate with the Hamiltonian. So let's explore this further. Consider a general function. Let's see. Let me start on a new page. Consider the time derivative of some function f that depends on the Qi, Pi, and t. Well, some function that you can calculate for the system. All right. So df by dt. Okay. So we're just going to apply the chain rule. So that's the sum from I equals 1 to n of di f by di Qi dot plus di f by di Pi dot plus the partial derivative of f with respect to time, di f by di t. Now let me insert the canonical equations into here. So the sum from I equals 1 to n. So remember, qi dot, that's equal to dih by dih pi. And pi dot is minus dih by dih qi. So I'm left with dif by dih qi times dih by dih pi minus dif by dih pi dih by dih qi plus the partial derivative with respect to time. Of course, you recognize this now as the Poisson bracket of f with h. So that's pretty interesting. The time derivative of a function of the canonical variables is given by the Poisson bracket with the Hamiltonian, plus some partial derivative with respect to time if that function depends explicitly on time. All right, so we have df by dt equals f, the Poisson bracket of f and h, plus dif by dt. So note this. If f does not depend explicitly on time, and the Poisson bracket of f with h equals 0, then f is conserved. Right? By conserved, I mean df by dt equals 0 if dif by dt equals 0 and the Poisson bracket of f and h equals 0. So I assume most of you are taking some, or have taken, or are taking some form of quantum mechanics. As you can see, this is very, very similar to questions of whether an operator commutes with the Hamiltonian. So in quantum mechanics, we speak of commuting. And so if something commutes with the Hamiltonian, it's conserved in time. And so here we see that it's not a matter of commuting, it's this funny Poisson bracket, which actually involves a sort of painful sum and partial derivatives. But you can fairly easily write a lot of the math out by just keeping in forms of curly brackets and get this deep insight about what's going on without after actually performing all these sums and partial derivatives. So there's clearly some connection here, obviously the quantum mechanics, and some connection between Poisson brackets, conserved quantities, and symmetries. So that's what we want to explore a little bit further. Any questions? Okay. So let's just do some, examine this further. So let's look at Poisson brackets and symmetries. So if you recall Noether's theorem, right, if the Lagrangian is unchanged with respect to some coordinate transformation or some symmetry, translation, rotation, whatever, then there was a conserved quantity Q, right? So let's look at, for example, angular momentum. So recall, for an infinitesimal rotation about the z-axis with an angle delta epsilon, we could write the infinitesimal rotation as x prime is equal to x plus fx delta epsilon. We found that that was equal to x minus y delta epsilon. So we found that fx was equal to minus y. Y primed was equal to y plus fy delta epsilon. We found that that was equal to y plus x delta epsilon. And so we found that this coefficient fy was equal to x. And then z prime was equal to z. So fz was equal to 1, or was equal to 0, sorry. I'm not going to bother to write out the time translation. And then we found that the conserved quantity so given that the Lagrangian is invariant with respect to its transformation, that's something you have to go and test. But suppose you found that the Lagrangian is indeed invariant when you do this transformation, then we found that there was a conserved quantity Q, which was given by the sum from I equals 1 to n of the Fi Pi, and that was equal to x times Py minus y times Px. And we also found that that was the z component of the angular momentum. Okay. So that's just a reminder of stuff that we've already looked at. Now consider this. Consider the Poisson bracket of x and Lz. So the Poisson bracket of x and Lz is x, and so so Lz is some function of the Qi's and the Pi's, right? So it's a Poisson bracket of a Qi with some function of the Qi's and Pi's. All right, so let me write out Lz as that function. So I have it above here. So that's the Poisson bracket of x with we have x times Py minus y times Px. All right. So that's, if you use the properties of the Poisson bracket, that's x with Py minus the Poisson bracket of x with y times Px. So I use the properties again now for when I have a product. So that's going to be equal to the Poisson bracket of x and x with Py plus py in the Poisson bracket of x with x minus y times the Poisson bracket of x and px minus px times the Poisson bracket of x and y. Okay. So now most of these terms are 0. X with py is 0. X with x is 0. X with px is 1. And x with y is 0. So you have to go back and look at the properties that we wrote down for the Poisson brackets. And only Poisson brackets that mix coordinates and or generalized coordinates and generalized momenta, the only non-zero one is the one that takes the generalized coordinate with its conjugate momentum. Okay? So this whole Poisson bracket is equal to minus y. So it's easy to show that. You can do the same thing with y, and you'll get plus x. And so it's easy to show that x with LZ, we just showed that one, is equal to minus y. Remember, that was equal to fx. It was the coefficient of the infinitesimal transformation that leads to LZ being a conserved quantity. So if you do y with LZ, you're going to get x, which is fy. And if you do z with LZ, you'll get 0, which is fc. So it appears that if you take the Poisson bracket of a coordinate and a conserved quantity, so a coordinate, for example, x, conserved quantity, for example, LZ, it appears that the Poisson bracket give the coefficients of the infinitesimal transformation associated with the conservation of that quantity. We haven't proven it, we just observed for one specific case of angular momentum. Okay? But it's interesting that you take the Poisson bracket of a coordinate and the conserved quantity, and you find out the transformation that's associated with the conservation of that quantity. So it's easy to show that Px with Lz is equal to minus Py. It's easy to show that Py with Lz is equal to Px, and Pz with Lz is equal to 0. And so again, think of a rotation of the coordinate system, and if you do that rotation, then the momentum vector is affected the same way as the coordinate vectors. And so we say that the momentum vector transforms in the same way as the coordinate vectors. It's all rotated. And so this would also be the Fx for the momentum rotation. And so then it gives really how all the coordinates transform under the transformation that leads to that particular quantity being conserved. So this, we've seen that the Poisson brackets of all the coordinates with a conserved quantity show us, at least for angular momentum, that allow us to find the transformation that's associated with the conservation of that quantity. And so what we say is, or the mathematicians probably say this, we say that angular momentum, that doesn't need to be in brackets, we say that angular momentum is the generator of rotations. So think of the angular momentum as some function, and to this function you can do this thing called Poisson brackets, and then it gives you a transformation. So you have a function, you do the Poisson brackets to you, and then and it gives you a transformation. So we say that that function is the generator of that transformation. Okay. So let's do an example. This is 7.2 in the notes. So let's show that a charged rotating sphere precesses about the axis of a magnetic field. So let's say, this is going to be a terrible drawing. I have some sphere. Okay, that's not very good drawing. So that's a sphere. And it's rotating with an angular speed omega. And let's say that I have a magnetic field here that's in the z direction. So what so this sphere has a charge, well, let's call it little q. And what we're supposed to show is that the sphere precesses about the axis of the magnetic field. Sorry for that phone call. Okay. So what that means, precesses, means that the axis of rotation, I apologize for the terrible diagram. The axis of rotation precesses about the magnetic field. So it's like a spinning top. Okay? So we have to prove that. Well, we've pretty much given no information, right? So what we first need to do is write out the Hamiltonian. So the Hamiltonian in this case, H, will be equal to the total energy. The kinetic energy here is constant, so it's not going to influence the evolution of the system. So all we need to care about is, so T equal constant, so it's not important. And then V, the potential energy, is going to be something like mu dot B, where mu is the magnetic moment. All right, so the thing wants to align itself to the magnetic field. It can't because it has to conserve angular momentum, so it rotates. And so there's an energy in trying to restore the axis of the magnetic moment with the axis of the magnetic field. All right, I believe a lot of you guys are taking E&M, so I assume that that's straightforward to understand. So the energy is related, or at least potential energy is related to mu dot B. All right, and since mu, on the other hand, is going to be proportional to the angular momentum. Right, the magnetic moment of the thing is going to be in the direction of the angular momentum, right? So in the direction of the axis of the spinning top, and it's going to be proportional in principle to how fast it's going. So H is proportional to V, because we don't care about the T. And that's equal to L dot B. Well, sorry, it's proportional. And that's going to be proportional to the speed of the top omega times Bz. All right, so let's just leave it like that. So omega yeah, let's just leave it like that. All right, so I do the dot product. The B is only in the z direction, so the dot product selects out the z component of everything. And the magnetic moment is proportional to L, which is proportional to omega, and so the Hamiltonian is proportional to omega times Bz. Okay. So now we want to figure out how does the system evolve. So if we want to know the time derivative of some quantity, we spent some time showing that all you have to do is take the Poisson bracket of that quantity with the Hamiltonian. So I want to know how the z component of the angular momentum of the charged sphere evolves with time. So all I need to do is take the Poisson bracket of Lz with h. Now the only parts that matter in h are w or omega times Lz. Omega is some constant, so I have the Poisson bracket of a quantity with itself, which is equal to 0. So it appears that Lz is constant. So that the z component of the angular momentum is constant for the system. Let's look at the x component of the angular momentum. So again, I take the Poisson bracket of Lx with h. So that's the Poisson bracket of Lx times omega Lz. And then that's equal to minus some constant times Ly. Because I'm just taking the we just did an example, right, where we looked at taking the Poisson bracket of some quantity and the z component of angular momentum. And we found that that was equal to the coefficient of a rotation. Right, so that was equal to fx. So fx for Lx in principle is minus Ly, and maybe it has some constant in it. Well, presumably it has some constant because there's the omega there. So just to make the unit work, so we don't really care what k is. Right, but this is the generator of the rotation, right? And we already spent some time seeing how different vectors transform under rotations. That you could just take the Poisson bracket with the z component of angular momentum. Okay. So similarly, if you do the time derivative of Ly, you take the Poisson bracket of Ly with h. That means you end up taking the Poisson bracket of Ly with omega Lz, and then you end up with something like k times Lx, where the k is probably equal to omega, but in principle might have other constants in it. I'm pretty sure it's equal to omega. Okay. So now compare this with the equation for a particle in uniform circular motion. So for a particle in uniform circular motion, the x component, let's say it's a particle going around a circle of radius 1, and the x component of that particle as a function of time is cos omega t, and the y component is sine omega t, the y position. Right, that's just some particle going around in a circle. So x dot is equal to minus sine omega t times omega, sorry. And y dot is equal to omega cos omega t. So x dot is actually equal to minus omega y, and y dot is equal to omega x. So compare that with the equations we have above. So think of the angular momentum vector for our charged particle. So the z component of the angular momentum doesn't change. So the angular momentum makes this constant angle with the z-axis. But now the tip of the angular momentum vector does change, right? The x component is equal to, its time derivative is equal to minus the y component, and the y component of the tip of the angular momentum is equal to plus the x component. So the tip of the angular momentum vector traces a circle in the xy plane. So if the tip of the angular momentum vector for a charged particle is tracing out a circle about the z-axis, then that is exactly the definition of precession. And so the charged particle is precessing. Okay. Okay, so I'm going to take the last, I never know when this class is actually supposed to finish, because one of the schedules says it's supposed to finish at half past, and one says at quarter past. So today I'm going to go to almost half past, because I want to just finish this chapter. Okay. Any questions about this example? It's kind of neat because you don't have to really write out any equations, and you just have to use the Poisson brackets of the system and some understanding of rotations and symmetries to come up with this conclusion. So that was pretty neat. All right, so let's finish up more rigorously on Poisson brackets and conserved quantities. So consider now consider translations. We just did rotations. Let's do the easier case of translations. So for a translation about the x-axis, we have x prime equals x plus fx delta e, and fx is equal to 1, y prime equal to y, so fy equals to 0, z prime equal to z, so fz equals to 0, and the conserved quantity q was equal to px. Okay. So let's go again with our theme. Let's evaluate the Poisson brackets of the coordinates with the conserved quantity. So let's take the Poisson bracket of x with the conserved quantity, which is px. Well, this is a trivial Poisson bracket, right? So this is a coordinate with its conjugate momentum. And so that was equal to delta ij, right? If it's qi with pj, then it's delta ij. So that's equal to 1. So that's equal to fx. And then similarly, the Poisson bracket of y with px is going to be the same as the Poisson bracket of z with px. That's going to be equal to 0. So it's equal to fx, and fy, and fz. So again, we see an example of taking a Poisson bracket of a quantity with a conserved quantity and getting back the coefficients for the infinitesimal transformation that leads to that quantity being conserved. So momentum is the generator for translations. So consider more generally a function f so some function of the qi, pi's, and t's. We know that f with px, so the Poisson bracket of f and px, is one of the properties that we wrote down for the Poisson bracket is actually equal to df by dx. That's from the Poisson bracket properties. So consider how f transforms when you make a translation. So under a translation in x of a distance delta epsilon, f primed would be equal to f plus df by dx times delta epsilon, right? If you transform translate the axes, then f prime will change this way. This is just the Taylor series, effectively. And so we find that the variation from that transformation, the delta f, is equal to df dx times delta epsilon. If you want to write out f prime equals f plus delta f. So in other words, f prime is equal to f plus the Poisson bracket of f with h times delta epsilon. Sorry, f with px. I'm sorry. So px tells us not only how the coordinates transform, but also how any general function transforms under the transformation that preserves px, or that results in px being conserved. Okay? So the Poisson bracket with px tells us how all functions transform under translations in x. Now consider a time translation So the conserved quantity associated with time translations is the total energy. And it's also equal to the Hamiltonian, usually, in most well-behaved physics cases. So under a time translation, of a function f of the qi, pi's, and t's, f prime is equal to f plus df by dt of times delta t. Now, if di f by dt is equal to 0, then f prime is equal to f plus the Poisson bracket of f with h times delta t, which we can also call it delta epsilon. So the Hamiltonian tells us how a function transforms with respect to time translations. So far we've used specific quantities that we know to be conserved, such as total energy of the Hamiltonian, px for momentum and translations, or Lz for angular rotations. So now let's flip this around and think about it in the other way. We just have some function. So now consider a general function g, and I'm going to make it only depend on the qi's and pi's, so that I can always make this assumption about the g by dt equal to 0. So this function g is going to be what we call a generating function for a transformation. So we can define a transformation of coordinates given by qi primed is equal to qi plus the Poisson bracket of qi with g, delta epsilon, and pi primed equals pi plus the Poisson bracket of pi with g. So I'm completely free to do that, right? I can define whatever function I want, g of the q's and p's, and then I can say, well, I'm going to take the Poisson brackets of q and g, and I'm going to make that the term that how the q's transform, and I'm going to take the Poisson bracket of p and g and make that the term of how the p's transform. Okay? And so if we want to write out the properties of the Poisson brackets, you could also write this as qi plus di g by di pi delta epsilon. You can write the pi's as pi minus di g by di qi delta epsilon. So that means that for the qi, fi is given by di g by di pi, And then for the PIs, the FIs are given by minus dig by dqi. So we call G the generator of this transformation. So the Hamiltonian then transforms as H prime is equal to the original Hamiltonian plus the Poisson bracket of the Hamiltonian with the generating function times delta epsilon. If the Hamiltonian is invariant with respect to this transformation, then H prime must be equal to H. That's what invariant means. So if H prime is equal to H, that means the commutator of H with G is equal to 0. But that also means that the commutator with G with H is equal to 0, because these are negative of each other. What that means is that dg by dt equals to 0, and G is conserved. So I'll write out the last sentence, and then I think we're done. So if, the Poisson bracket of the Hamiltonian with some function is equal to 0, then the Hamiltonian is invariant to the transformation generated by G. Also, G is conserved. Question? Oh, how do we find G specifically? Well, that'll be the subject of the next chapter. But not easily. All right, so I'm sorry I went a little bit over time. I thought this was an important subject to close off, and we actually covered quite a bit of material today. I really wanted to leave you again with this concept of some symmetries or some invariance of the Hamiltonian or the Lagrangian with respect to some transformation or symmetry leads to a conserved quantity. And here we see specifically, using the mathematics of Poisson brackets, how all you need to do is test if the Hamiltonian is invariant, or you test that the Poisson bracket of the Hamiltonian and the generating function is 0, and then you know how to find the conserved quantity, as well as the transformation. Yeah, Jason, you have a question too? I assume you guys are getting kicked out of class, if you're in class. Yeah, let me get back to you by email, Jason. Any questions? Okay. anyone sure has a question? All right, okay. Thanks. So I'll talk to everybody on Monday. Bye.